This is 4.3 day 3. Okay, some of the word problem ones. So 67 asked us about the insect population can be modeled by this equation. It asks us in part A to what is the horizontal asymptote. So horizontal asymptote is this imaginary line right here. Remember, when they are equal degrees, it's at 10 over 1 in this case. So it's at 10. So right here at 10 is our horizontal asymptote. Part B, determine the initial population. So our initial population is at 0 months, so right there at 1. And since it's in millions, it'd be that means 1 million insects. Okay, part C, what happens to after several months? Okay, so in the early months, you can see it increases quite a bit, and then over time it really levels out. Okay, so it levels out and it gets close to and approaches the 10 million insect mark. But since it's an asymptote, it'll never really reach that. And then interpret the horizontal asymptote. It's our limit of our population, right? So our population will get closer and closer to 10 million, but it will never actually reach 10 million, so it won't go over 10 million insects. Number 73. 73 gives us this function here, and if you graph it, it tells us that it's limited to just the positive, x is positives. So we have the railroad track and how much it has to bank in order. So if I have a tight curve, it has to be a little bit more banked, but if I have a wider radius turn, it doesn't need quite as much banking. If you think about a race course or even on the road, if you have a real tight corner, a lot of times they bank it so that the outside part is up higher. Okay, so at f of 400, 400 is the x, your radius. So at 400, you plug this in here, you get this. So it's saying that if I have a radius of 400 feet of that curve, I would need to bank it, the railroad track, 6.35 inches. Okay, part B, how does it change? Okay, so as the radius gets bigger and bigger, the amount of bank I need gets smaller. But if I have a small radius, okay, small radius to my circle, which means a tight corner, I need a more banking to it. Okay, so the more gradual the turn, the larger the radius, the less bank needed. Okay, part C, interpret the horizontal asymptote. So we have a horizontal asymptote. Remember, if the degree is higher on the bottom, it's at y equals 0. So it just means that it's going to approach a bank of 0, and we're never going to have a negative bank, because then we would have a radius on the other side. Okay, part D, elevation of 12.7 inches. Okay, so we want to know, where does this equal 12.7 inches, right? So if you come over here, I use Desmos for it, it'd probably be the easiest way, or you can just take this y and plug it in there and solve, both works well. You would get right here at a radius of 200 would have that bank. Okay, 78 gets into the direct and inverse and joint variation stuff. Okay, so it says p varies directly with the square of, p varies directly with the square of z, and inversely with the radius. So then it gives us some values. It says that p is this, r is this, and z is this, so you put those numbers in there. And what I did was I used cross multiplying, so that times that is equal to that times that, and solve to get k is equal to 4. Then it gives you some other values. Okay, so find the p when we know what our k is, so we put our k into this equation here, when our r is a 2 and our z is a 2 and our r is a 16. So we plug those values in there, work it out, you get p is equal to 1. Okay, number 80 says y varies directly with x, so kx, and inversely, so on the bottom, of m squared and r squared. Gives you these values, plug them in here, and work it out to k is 60. And then once you know 60, you can plug that into this equation with the other x's, m, and r's, and work that out to get 180 over 64, which simplifies to be 45 over 16, which is 2.8125. Okay. Number 82 says that our k is positive, so that's kind of important there. But it says as y varies inversely with x, so y varies inversely with x, we know what this equation looks like, right? We've been studying these. So this equation looks like this, right, for our positive x's. So as x increases, as x gets larger, the y decreases. And as x decreases, as x gets smaller, the y will increase. Okay. You could also put some numbers in there and work them out and see what happens to them. Okay, 84. So I did 83. You didn't have to do 83, but I did it by accident. So I just have it here for you. As x doubles, so if this number doubles, this number is going to get half. So let's say there was a 1 there. If I double that to be 2, okay, so we could use this idea. Let's say I use, k is a 1. Okay, so if I use those numbers there, if I double this value, so if I double this value, y would be half, so it'd be half of that amount. Okay, so you can kind of plug numbers in and play with it as well, if you can't necessarily see it there. If x doubles, okay, what will happen to y? Okay, so one thing you could do here is let's just take some numbers and plug them in. So let's say that our k is a 1, it's easy to do. Let's say x is a 2. So it would be 1/4. So my y would be 1/4, right? So if I think about this, when my x is a 2, my y is a 1/4. Okay? Now, if x doubles, so if x doubles, let's say we double it and make it 4. So my y would equal, keeping my k the same, okay, so it'd be 1/16. So you can see that this gets this is 1/4 the amount of, so if this doubles, this goes 1/4 of the amount. And you could use other numbers, it can be any numbers, just take a number, plug it in, and see if it doubles. Okay, so number 86, if x is halved, okay, so there's our equation first, okay, directly proportional to the second power of x. So let's just pick some random numbers again, right? So let's say that my y is going to equal, we'll just keep k as 1, and let's use x as 2. Okay? So if I know my x is a 2, 2 squared is 4, 4 times 1 is 4, right? So I'd have 4. Now it says if x is halved, if I take that and halve it, so it's a 1, my y would equal this then. 1 squared is 1, times 1 is 1. So how did this change? It's 1/4 of the amount that it was before. And now it would work with other numbers, any other number as well. Okay, number 88 talks about natural gas. It says the volume of a gas varies K over P, and directly, so times T, the temperature. So it gives you these, that the volume is this, and the temperature is that many kelvins and 18 newtons. Okay, you plug that in and solve it, you get this is your K value. And then they say, what if we raised it to this and this? Okay, so you use that K you found there, plug them in here, and you get your V. Okay, number 90, same process again. Okay, resistance is equal to K times the length divided by the radius. Okay, you can plug those in there and solve for your K, and then plug in the other values to find the value you want. And number 92, the brightness or intensity of starlight varies inversely as the square of the distance from Earth. So the farther I get away from Earth, the more I can see the stars, right? The more intensity. Okay, so this is the equation there. So I kind of think if K is going to stay the same, it says a Hubble telescope can see stars whose intensities are 1/50th of the faintest star. See, the intensity is 1/50th. And if I keep my K, constant, and if I basically just solve this equation, then I get d squared is equal to 50. Okay, so when I solve that, take the square root of both sides, can't have negatives, so it's just 7.1 times. So the Hubble telescope can see 7.1 times farther in space than what we can here on Earth.